Okay, hi everyone, it's Mr. Chernetsky here, just setting up. Let's see now. How do we do this? Page view. Okay. Okay. Hello everybody. Today we're going to talk about oscillatory motion. So this is the... Let me start again. Hello everyone. This is the first in a series of lectures about chapter 15, where we'll be talking about oscillatory motion. This is the first chapter in the Waves, Optics, and Physics course, and while it has very strong ties to sort of physical objects, motion, stuff we may see in everyday life, it also serves as an introduction to the formulas and descriptions of oscillators in general. So that's why we'll begin with these examples of things that are easy to picture and talk about, so that once we get to more advanced stuff like quantum mechanics, this understanding of oscillations and mathematical descriptions will already be secondhand to us. So right off the bat, the first thing I want to talk about is the simplest oscillating system that we can describe without too much hassle is simply a E-block on a spring. Now, if you look at the system here, the position in the middle, position B, would be the equilibrium position, which is the system being undisturbed. So we have a mass attached to a block, attached to the wall, and if you don't pull or push, then it will just remain there. However, if you were to stretch the block or compress the block, as you see in pictures A and C respectively, then the moment you let go, the spring will jump in the opposite direction. For example, in part A, if you stretch the spring, it will accelerate and move back towards the left side. If you compress the spring, then it will actually jump back to the right and stretch out. What's happening actually is that when the spring is compressed or stretched, it exerts a restoring force which points opposite to the stretch or the compression. So if it stretches towards the left, the restoring force wants to push the block spring system back to the left. And if you compress this spring block system to the right, like in figure C, there will be a restoring force acting on the block from the spring that wants to push the block back to the right once it's released. This restoring force is actually proportional to the displacement of the block from its equilibrium position. So it's then a matter of being able to have a ruler handy and measure how far from equilibrium the block is displaced to understand the strength of the force. You may have already seen this in introductory physics. The force is essentially proportional to the displacement of equilibrium times a spring constant K. This force is called Hooke's law. And then it stands that the farther you stretch the spring from equilibrium, the stronger the restoring force. So by Newton's second law, then, the restoring force is equal to the mass of the block times the acceleration the block undergoes at a certain displacement from equilibrium. We are not worried about the mass of the spring in this simple model. So with second law, here you can isolate and talk about the acceleration the block undergoes, which still, again, proportional to this displacement from equilibrium, and we have the spring constant divided by the mass of the block, both really just constants. In differential equations, the acceleration is the second derivative of the displacement with respect to time. And what we're going to want to do is we are going to want to describe the motion of the spring block system, because as it stretches and compresses, the restoring force makes it swing back the other way. It'll be stuck in the cycle of being pulled into a stretch, and then the restoring force pushes it back into compression, and then it springs back out, and so on and so forth. So there's a few reasons why kinematics formulas that we used before don't work, but number one being that this object basically oscillates between two positions back and forth. So it's not a linear or cubic or any sort of incremental increase in displacement, but it's something that just keeps going in a cycle. We can refer to the constants k and m with this single term omega. We shall get back to it later, but it is essentially a property of the system since it depends on the spring constant k and the mass of the block. So I'll just note that. So the second order derivative with this new constant omega is equal to negative omega squared times the displacement. And we have what's called a second order differential equation, which we can solve and get a general formula for the displacement as a function of time. The way you solve this is for a calculus course, so we won't get to that, but the solution is in fact a trigonometric function using the cosine, but you can also use sine as well, since sine and cos are shifted by a phase of 90 degrees respectively. I'll put up a primer soon that sort of discusses trigonometric functions, since we'll be using them quite a lot during this course. Now, this being a second order differential equation which is solved here, we can then talk about the first and second order derivatives using the solution that we found. So this is second order and now we have three equations, one for the position, one for the derivative, the rate of change of that, and then the second order derivative of the position. Note that the only variable here is time. As such, when you take the derivative, you end up with a sine and then a cos again once you take the second derivative, and there's a negative sign in front of both. Now, you'll note then that now there's another constant thrown in, which is the phi here. We'll get to that soon. So, quick quiz here. Let's say a block on the end of a spring is pulled to some amplitude A, and it's released from rest. And in one full cycle of motion, how far does it travel? So when we talk about being pulled to position A, right, that always stands for sort of amplitude of the oscillation it'll take on. The spring will compress and stretch up to an amplitude of A. So if you stretch it by 5 meters, it'll swing back and compress by another 5 meters, and then jump back out, stretch again up to 5, and then compress back, so on and so forth. But in a full cycle is really just how long it takes to go back to its initial position. So if you consider the block in its initial position has been stretched past equilibrium to a distance of A, and we suppose then that the equilibrium position is somewhere in the middle. So then it'll kind of get pushed back, kind of compress to a distance of x equals -a, and then it'll have a restoring force that'll push it back to the right into a stretch. And at this point, we will have completed one cycle. So in this time, what we've gone from a position at x equal to a all the way to -a, and then from -a to a. So we made 2 trips through, which means that the total displacement would be 4a. And just to show you here, I'm gonna include the forces at each point in time. So when the spring is stretched like this, it has a restoring force that points to the left. And when the spring's compressed, it has a restoring force that points to the right. And then at this last drawing here, then the spring will once again move to the left, accelerated by the restoring force. Now, the general form of the position of a spring, like I said, it's a cosine function. And the cosine function is here because it doesn't go any bigger than -1 or 1, right? That's like its range. So it's great to use it for the position of a spring block system because the spring block system only goes from an amplitude of a all the way to -a. The term omega is in fact the angular frequency, and the phi term is the phase shift. So let me note that for you. What the angular frequency determines is basically how fast the system oscillates. So the faster it moves back and forth, that means it has a much bigger angular frequency than a slowing moving spring block system. The units of angular frequency are radians per second. And the phi term I was talking about is just called the phase shift. We'll talk about it a little bit later, but basically it's there to account for the initial conditions of the spring block system. Because at initial conditions or displacement function, t is equal to 0, so the cosine function will just depend on the phase shift to let us know what our initial position is. So we have 2 graphs here on the right. The first one just shows, again, some position versus time graph for some spring block system. And you'll note then that over here, the y-intersect, right, that's at the starting point that t is equal to 0. This means that the block starts off not quite at full amplitude, right? This is this being still at a state of being stretched because its displacement's positive, but it's not at its full amplitude. And at this point in time, if we press play, the spring block system moves towards compression and ends up sometime later being compressed over here back to an amplitude of -a. And then this keeps repeating cyclically while after an instance of max compression, it kind of swings back up to a point of maximum stretch before getting pulled back by the restoring force into another compression, and the cycles just keep repeating that way. Now, if the phase shift term is equal to 0, like the graph B here at the bottom, then what you end up having is a much simpler displacement formula where the cosine, the output of the cosine just depends on whatever the angular frequency is and how much time has passed. And you remember that cos of x starts off, at +1 and then dips back to -1 and then just kind of repeats that. So it has the same shape since there's no longer the phase shift. You can also think of the phase shift as a horizontal shift, since it'll move the drawing of the graph left or right depending on its value. So we showed the two derivatives of x, and that is essentially or velocity and or acceleration. After all, that's by definition velocity and acceleration, right? It's a rate of change for displacement, and acceleration is a rate of change of velocity, which is the second order derivative of displacement. The formulas look similar to that of displacement, but there is a negative sign in both, and there's also a angular frequency term in the speed, in the velocity equation, and for the acceleration equation right below it, we have the square of the angular frequency as well. Because, again, these are trigonometric functions, they have sines and cos, which only go from -1 to 1, so they have like maximum values, which occur when sine is equal to 1, or when cos is equal to 1 at a particular point in time. That's as big as their trigonometric functions can go, and when that's equal to 1, then that will give us the biggest value we can get for the velocity and acceleration of the block. And I should actually say that in this case, because there's already a negative sign here and here, then the maximums will occur when the sine and cos give you a -1 respectively, so that the actual output for Vmax and Amax is positive. So the maximum speed then is when the sine term just goes away and you just have the angular frequency times the amplitude of the oscillations, and that's as big as the velocity can get. And so with the max acceleration, that's the omega squared times a. And because the motion of the spring and block is always taking it through different positions, different displacements at different points in time, then but also the speeds and acceleration are not constant. Depending on where you are in the motion, your speed and acceleration might be between 0 or their maximum values. So here we're basically showing you the same system, the same mass spring system with its respective position versus time graphs, velocity versus time, and acceleration versus time. You'll note that the amplitude, the max amplitude, is right over here, and then our starting point isn't quite the max amplitude, but in a short time we do get there. So you can imagine then that this system starts off kind of getting pushed to the right towards a position of max amplitude. We're not quite there yet, but we're definitely on the positive side of things. We're past equilibrium. Now, then, because we have, right, we are at some displacement that's positive, by Hooke's law, we expect then the restoring force to be negative because we are at a positive displacement and there, right, remember that the restoring force is equal to negative kx. So for a positive x, let me, I do that wrong. My bad. For a positive x, then the restoring force is negative. So if we had to draw the restoring force, if, sorry, I kind of mumbled that. If we had to draw the restoring force, then we'd see that it's pushing this way. And likewise, then, by Newton's second law, that's proportional to the acceleration. So expect acceleration to be pointing left, which is negative. And as for the speed, well, if we look at the position graph, we see that it's about to reach, it's going towards max displacement over here, right? So it must be moving to the right. And that must mean then that at least at t is equal to 0, the velocity is positive. So at least initially. Because again, what I'm showing you here is a snapshot of the initial sort of condition of the system. So now I can get into the two remaining graphs with a bit more clarity, right? So the velocity versus time graph shows what I was talking about. So that's graph V, right? So our initial velocity is positive, it's to the right, but we're soon approaching max amplitude, a full stretch, which means we're going to be swinging back to the left. So that's why the velocity drops to 0 at a max displacement once we reach an amplitude of a, and then we'll swing back, and once we just pass equilibrium, actually that'll give us our max speed here, which occurs again at equilibrium. And then the same thing is shown here, where at this point we were passing equilibrium again, but this time we're moving to the right. About to reach that point of max stretch, which we already did a cycle ago. Now, what happens to the acceleration during this time? If we look at the point of interest, which would be when the position is at max amplitude, the acceleration is actually magnitude-wise, it's at a maximum, but it's going to be a negative acceleration because at the state of being fully stretched, it's going to want to accelerate the block all the way back to the left. Then you see the acceleration starts to decrease towards 0, and this point here is the equilibrium point. So as the block passes through equilibrium, it's no longer stretched or compressed, so there's no restoring force. But even though it's not accelerating then at this point, it's still moving because it has been accelerating, right? At this point in time, as you can see in graph B, that's when the velocity, when speed is maximum towards the left. So it'll still keep moving back to a point of full compression. So it'll compress all the way to its full amplitude, but in the negative direction, at which point the restoring force is once again maximized, but this time towards the right. So it'll accelerate all the way to the right. It'll pass through equilibrium, at which point the acceleration is 0, but it still has speed to move all the way to full stretch. And then at full stretch again here, it'll start to compress back. So that's all I wanted to talk about for this lecture. I hope you join me in the next one.